हमने तो वो हड्डी हड्डी तो वो पिछले पदार्थ पे ही हमने छोड़ दी। अरे बाप रे, तो एलियंस हमें फॉरएवर रहना।
So this is what we did last class, integrating factor, and we find the solution of linear first order equations. Okay, so there are also some differential equations which you can reduce to this linear form. Okay, like we did in the previous case. So here also that some special first order equations. Okay, some special forms which you can reduce to the this linear first order form. Okay, so the first one, or we will say equations reducible to linear form. Equations reducible to linear form. So I will give you the examples of one equation. This form is known as the Bernoulli's form. If you have this type of equation, then you can easily reduce it this one, and this one is known as Bernoulli's equation. Okay. Now you see the equation is of the form dy by dx is p of x y, and then we have q of x y power n. Okay. And this n not equals to 1. Okay. So here you see, if you have the equation of this form, this is known as the Bernoulli's equation, and you can easily reduce it to the linear form. Okay. So how you can do this? This one is given by the Bernoulli, James Bernoulli. So the name Bernoulli equation. Now you see, it's easy if you can, if you put n equals to 0. Okay, then it's simply it's a linear form. Okay, and for n equals to 1, what happens? That also you can reduce. Okay, now here you see, for the higher values of n, what we do, we will divide each side by y power n. Then we will have y power minus n dy by dx plus y power. So here 1, so minus n minus 1. So here, if you divide it, it will be p of x, and we have q of x. Okay. We'll make
Ma'am,
it,
that will
sorry,
be
1 minus 1, 1 minus n, sorry. 1 minus n. 1 minus n. Okay. So you see, by simple substitution, you can do it. Okay. You substitute y power 1 minus n as z. Okay. See, you have to change it to the linear form. So here you must have px and 1, y power 1, or whatever variable. So simply if you substitute this one equals to z, what we will have here? What will be dz by dx? So 1 minus n, y. Here 1 minus n. So we will have, how much we will have? Y power minus n,
minus n.
minus n dy by dx will be equals to dz by dx. Okay. Now if you substitute, you see y power minus n dy by dx. So here it will be dz by dx. We have here 1 minus in the denominator. Okay. So we have 1 by 1 minus n. Okay. Now this one is that p of x y power 1 minus n we have substituted here as z, and this is q of x. Okay. And you can multiply this 1 by 1 minus n is the constant, so you can multiply and it won't impact anything. Okay, dz by dx. So you can see since it's a constant, now this is your equation. Okay, now you can see it's a linear equation. Okay, and you can solve it like by the previous method. So this is a linear equation. So it's a linear equation. Okay. And we know how to solve this linear equation. Okay, by our previous method, finding we have the integrating factor. Okay, so one example, let's do. So dy by dx plus y by x, and here we have y square by x log x. So what we will do here, we will divide this y square on both sides. So we will have y power minus 2 dy by dx, and here it will be y power minus 1 and x power minus 1. Okay, or we can write it 1 by x squared, and here we have log x by x. Okay, so what will be the substitution? Okay, 1 by y will be our substitution z. Okay, then what we have? What we have? Y power minus 2 minus dy by dx, and this will be dz by dx. Okay, so this is our substitution. Okay, so here if you substitute, we will have minus dz by dx plus 1 by y is z, so z by x and log x by x. So if you want, you can multiply it with a negative sign and you can find out. Okay, and you know how to solve. This is a linear equation now we have. Okay, you can solve this one, find the integrating factor and solve it. So solve it if you want. Like the previous method, you will solve it. Okay. Now do one more problem. Okay. The linear first order equation, so you can solve it. So now the next one. We are able to reduce it to x divided by dx minus x plus 1y wait a minute. Okay, so the previous one, what was the, okay, I will come to this one. Any of you done the solution for the previous one? What is the solution for this one? Just tell me the solution and I will write down. What is the integrating factor here?
1 by x.
1 by x.
1 by x is the integrating factor. Okay. So here, if you write it, dz by dx minus z by x minus log x by x. So the integrating factor, if you see, p dx, so e power minus 1 by x. So you have log x and minus sign is there, so 1 by x is the integrating factor. And what is the solution? Done anything? It's z by x equals to 1 by x log x. So you will find it. Okay, I'm writing here. Once you have the integrating factor, it's easier. Plus 1 by x plus C, or you can write also Z is 1 by Y. So that also you can put it. Okay, X will get cancelled here. So 1 by Y goes to log X plus X plus. So this will be, this is 1, not 1X. Okay, so this is your solution. Okay, you have to find it. Okay. So you can do it this way. Okay, I'm not doing much. Okay, we will move on to the next part. Okay, so next part is so here it is the welcome to the second order differential equations with constant coefficients. Okay, second order differential equations with constant coefficients. Okay. Okay. So here we will methods of solution of linear equation. So here we will talk about the differential equator or the differential operator. Okay. So the differential operator we will be talking about. D. Okay. Differential operator D. So it's D. Okay. So this D equals to d by dx. Okay. So sometimes it's easy to write in this D form. Okay. And so if you say here d of f of x, if f is a function of x, then you can also write f dash. Okay. We used to write df by dx. Okay. This is df by dx. Okay. So this d we are going to use very much. Okay. It's like d of x power n. So it's the d by dx. You understand that it's the first order uh, derivative with respect to x. Then we will have this much. Okay. D of cos x minus sin x. Okay, so this is how you will understand this one. Okay, and if you look at the properties of the, it's a linear one. Okay, suppose you have this one, a and b are constants, then you can take it out. Okay, so it's linear, so we can use this one. Okay, this d is linear. Okay, so this because d is a linear operator, so we use its differential operator. Okay, so we use the term operator. Then we have here. So this is the first order dy dx. Okay, now you can write it this way. Okay, so this one will be derivative of f dash. So this will be the second order derivative d by dx of f dash. So it will be f double dash. Okay, so this we use for the second order derivative. Okay, we used to write d power 2 for this. So this d power 2 is the second order derivative. You can see. Okay, this. Similarly, we have d cube, and the powers of d will give you the order of the derivative. Okay, suppose we have this d cube f, so it will be the third order derivative. Okay, or you can say, yeah. So it's the third order derivative. Third order derivative with respect to x, and this is the second order derivative. So this is how d4 means fourth order derivative. Okay, so we will be writing the terms with respect to this differential operator, and here the minimum possible is d0, and this is that means 1. Okay, so no, we are not differentiating this one, so it's 1. Okay, so here you see we will be writing this one. Okay, suppose we have this equation d square y by dx square plus 5 dy by dx plus 6y equals to 0. So what we will be write here? So we will be write here. This is the second order derivative y equals to fx 5 dy plus 6y equals to 0. Okay, or we are actually we can take the it common. Okay, the y. Got it. So this is how we used to write. Okay. Now solution here, if you find how the solution will come. Okay, so this is how we represent the questions also. Okay, instead of they're equivalent. This one and this one, they're equivalent. All the terms are equivalent. Okay, only the representation is different, but they're same. Not only equivalent, they are also same. So they are equivalent. Same actually. Only the representation is different. I will not say equivalent. Okay, they're same. Only the representation is different. Okay, we can also factorize. Okay, suppose we you are writing it like this, d cube minus 6d square plus 11d minus 6. So you can factorize this one also, d minus 1 into d minus 2 into d minus 3. So this way you can factorize also this operator. Okay, like suppose you have y, so any one operator can act in y. Okay, d minus y, then you can leave it. Okay, like this d minus 3, you can say dy minus 3y. So dy will be one order differentiation. Then again whatever you are getting, then you operate with this one, then with this one. So that will be the easier one. Okay, now we will look at the what I have said, second order differential equation with constant coefficient. Okay, we will go for the homogeneous one. Okay, we're talking about here. Let's see first for the homogeneous. Okay. Now here this homogeneous equation of second order. Okay, how it will look like? Linear homogeneous second order equation. Linear homogeneous second order equation. Okay, linear homogeneous second order equation. So this will be of this form. Okay, and here we will say this A, B, C are constants. Okay, so here we have a function of d, we can say. So you see, this y dash means the second order derivative d square y by dx square. So you can write it in this form: d square y plus b. It's the first order derivative dy plus cy equals to 0. Or as I said, you can take common this y. Okay. This one. Okay. So this is how you can represent this one. Now here the solution. Okay. So when we talk about this equation solution, we will have general solution. Okay. So we will talk about the general solution. Okay, or the you can say the particular solution here we will have. Okay. So whenever we have this type of form here, this one, we can write it in this form. So this equation, the solution when we are talking about, okay, we will have some natural form. Okay, for the first order equation, okay, when we have y dash plus my equals to 0, we have the solution y equals to plus c. Okay, so this one, I don't miss this one, so we should do a little bit for the solution part also. Okay, solution of linear differential equation. So in the solution, you have, so we will have the particular solutions. General solution will consist of, here we have in the right hand side 0. So we will have the general solution will consist of, one is the pi, the particular integral, and one is the into directly. Okay, let me tell you this one. So y equals to e power minus mx plus c. Okay. And the solution of the equation y dash minus my equals to 0. So here the solution will be y equals to e power mx plus c. Okay.
Ma'am, what is M here?
M is a constant here. M. Wait a minute. This one is for the first order. What I've written, you can see it's the first order one. Okay. So here you can do this one. If you find out the solution yourself, okay, and you will be getting a solution. Okay. So it is natural to try for a particular solution of the form y equals to e power mx. Okay. It's the first order differential equation. Okay, like we have. Sorry. Okay, so this is the first order equation, and you already know how to find the solution. You can find this one, how it will be. Anyone done? Just find it, whether you are getting this or not. I want to see. Simple one. Okay, it's a very simple equation. You try and do it. I would like to know whether you are getting this.
Ma'am, that constant will also have e to the power minus mx as coefficient.
This c is a constant of integration. This one, and it's a y dash plus my. This m is a If you have a first order equation, you will have the first order differential operator dy by dx. Okay, this is first order differential equation. Okay, so if it's a first order differential equation, we will have dy by dx. Okay, and there will be y term. Okay, and we can have the constant here. Okay, got it? You can also have other constants. So how you will solve this one? Y is y equals to f of x. Y means y equals to f of x. If you want, you just we did that form. This is p y q p x q x form, that you can do also. That is the easier one. This m you can consider as p of x, which is a constant. Okay, and this one you can see. If you are getting confused, simply you do this one. So what we have, the integrating factor will be e power
e to the minus x minus mx.
right. So it will be
E
minus
power mx.
mx, right? So
No, ma'am,
you can
mx.
direct mx. This is plus, right? So it we have e power mx. What was the form? dy by dx plus my equals to 0. Got it? So you are getting it. Now you put it in the form. What was the solution? So you can write it as e power. The
It
form I
will
told.
coming as c into e to the power minus mx, not plus.
Yes, ma'am.
C.
Multiplied by
Yes, ma'am.
constant into e to the power minus mx. It is coming.
C into e power minus mx.
I
Okay.
equals c into e to the power minus mx. It is coming like that.
So it's a constant. You can and the constant of the constant of integration. Where is that?
Yes, ma'am. C is the constant of integration.
Wait.
Ma'am, we can use variable separable method.
No, you can use that also. Whichever way you use, you should be getting this one. Okay.
Ma'am, in the integrating factor 1, ma'am, how do we integrate 0? Because
0.
0.
That will be 0.
Ma'am, then I don't know where to put c exactly. It's coming y into e to the power mx equals to 0.
Okay, let me give you this one. Okay. Y. So we used to do this one y p dx. So p dx we will put it mx here. It doesn't matter. Okay. So since it's the constant of integration, so we have here mx. Okay. And this one 0 plus c. Q is 0 here. Can we write it like this? Q is 0, right?
Yes, ma'am.
So we can write it like this. So y will be how much?
C into e to the power minus mx.
Minus mx. Okay. And this c is here, so don't get confused. It's a constant of integration, right? So you can put it like this. There is no issues. You were saying, right, where you can also put it like this way. So it's a constant, so we can adjust it with itself. But so we will put it since we are doing the integration. See, you can directly also do integration. Take it this way and do the integration. Okay. So what we are getting, this is the constant of integration. So we can put it this way also and that way also. Got it? Instead of that, you can go for this logarithm. Okay. So that way also you can get it. But we can write it like this. Okay. So this is how you get the solution of the differential equation. Okay. First order one. Now we will see what we will do for the second order. Okay. So now for the second order, it is natural to try for a particular solution of the form y equals to e power. We're trying to find the solution of the form y equals to e power mx. Okay, where m is unknown constant. Okay, if you have the initial value problems, you can determine that value. Okay, So this m is an unknown, but it's a constant. Okay, when I'm saying this one, we are actually trying to find a solution of this form. Okay, it has certain benefits. That's why we are putting it in this form e power minus mx. And here this m, it's a constant but unknown. Constant. Okay. Now y dash can be m e power mx. Y double dash can be m square e power mx. So this is the form. Okay. So here actually first we will find the characteristic equation or the auxiliary equation. Okay. So how we will find this one? We have this a d square plus b d plus c y equals to 0. So here what we try to do, we will substitute, we will put d equals to m. Okay. So what we are finding here, a m square plus b m plus c. Okay, and this equals to 0. Okay. Why? Because as e power mx is always positive. Okay. So and y is the solution, y will be of the form e power mx form, right? So here when you have, we can get it, and this one is known as the auxiliary equation or characteristic equation. Or characteristic equation, and here after solving that you will be getting the solution, characteristic equation. Okay, am square. So it is easy, you see, simply we are substituting d as m in the equation, and since y it's not equals to 0 because we have the solution of this form. Okay, so here this is positive, okay, exponential, so we are getting this equation, and this one is known as the auxiliary equation. Okay, this is auxiliary equation or characteristic equation. Okay. Simply we are replacing this d by m, or you see the first order derivative will be by m. The second order derivative will be by m square. So this is how, now you have to find the roots of this characteristic equation. Okay. So they are known as the characteristic equation root. So the roots of this equation, the roots of this equation are known as characteristic roots. And we have a form, we will put this one as characteristic roots. So the quadratic equation, it's a quadratic equation, it's a second order one, so it will be the quadratic equation. So the solution will be, so the quadratic equation has the roots. So you can put that formula, okay, for the quadratic equation, m equals to minus b plus and minus b square minus 4ac by 2a. By 2a. Okay. Now you see, we will look at the types of the roots. Okay. First, you can have distinct real roots. Okay. So the roots, real distinct roots. Okay. The roots are real and distinct. So looking at the type of roots, you will get the solution. The roots are real and distinct. Okay. Say m equals to m1, m2. They're distinct. Okay. So m1 not equals to m2. Okay. And what that means, when we will have real and distinct roots? Okay, we assume that b square minus 4ac is positive. Okay, then we will have real and distinct roots. Now the second one, the roots are real and equal. That means the repeated. Okay, so the roots are real and equal. Okay, so you can say m equals to m1, and when this happens, if this here it is greater than 0, and if you have this equals to 0, then we will have the repeated roots. Okay, when b square minus 4 is equals to 0, you will have the repeated roots. Then the last possibility is you can have the complex roots. The roots are complex, and you know if the complex root occurs, they occur in conjugates. Okay, it's a quadratic equation. So if one root is complex, the other one has to be. So the roots are complex if b square minus 4ac less than 0. So here complex. Okay, so these are the three possibilities for this quadratic equation. This one, am square plus bm plus c. And you see correspondingly how we are going to get the roots. Okay, I will derive for only one, and the rest you will derive if you have real and distinct roots. So if you have real and distinct roots, okay, and we have assumed they are m1, m2. Okay, so now we obtain two solution of the equation. Okay. So now we obtain two solutions of equation 1. Okay, that is am square plus bm plus c as e power m1x and e power m2x. Okay, so the two solutions are linearly independent because m1 and m2 are not equal. Okay, so how to find this one? Let me tell you. So see, it's a quadratic equation. Okay, and we have seen for the first order we are getting the solutions like this. So we can say here, okay, since the roots are distinct, we can say roots are distinct means see this am square plus bm plus c. If m1 and m2 we are able to, so here actually you will be getting of this form, right? In this form, so this is a linear and this is a linear, so that's why we can have the solutions of the form e power my m1x and e power m2x form. Okay, so this two roots we have, so the solutions can be of this form, e power m1x and e power m2x. So now the two solutions are linearly independent. Okay, the two solutions are linearly independent as this m1 m2 are not equal on any interval I. Now if you look at the Wronskian, how you will get, okay, let me show that the Wronskian is not zero. If y1 is e power m1x and y2 is e power m2x, okay, let me show you the Wronskian. So this is one of the way to check whether it's linearly independent or not. Okay, so this will be y1 y2 dust minus y2 y1 dust. So y1 m2 e power m1x e power m2x minus m1 e power m1x e power m2x. Okay, because y1 is you consider e power m1x and y2 is e power m2x. So y1 e power m1x and you go for the derivative, we have m2 into e power m2x. Okay, so here right. So since we are assuming two solutions, so you assume y1 equals to e power m1x and y2 equals to y1, y2 are solutions. Okay, so then we can write it like this. Now since m1 and m2 not equals to 0, this is m2 minus m1, and here this one is common, we can take this part. So you see this is exponential, so this part not equals to 0. Now this is also not equals to 0 because m1 not equals to m2. So this total expression is not equals to 0. That means the Wronskian is non-zero. Okay. So here now we can look at the general solution. Okay. They are not linearly independent. So hence the general solution. Of equation 1, the second order homogeneous differential equation is, you can add, okay, since there are two we have two linearly independent solutions, so the general solution will be, we can add this one. Okay. Okay, so this is the general solution here. For any looking at this real and equal roots for also you can get it. Okay, so for the real and equal roots are obtained for the character equation when b square minus 4 is equals to 0. So we have repeated roots. Okay, I will only write down here. So here we have the equations of this form. Let me write down, then we'll solve real and equal
Excuse me, ma'am.
roots. Yeah.
Ma'am, in the process of derivation, please explain once again from W of x and y. Yes, ma'am, from that point. Yeah, ma'am.
So this is linear. If this is linearly independent, both the solutions, you can get the general solution as the sum of both the solutions. Okay.
Ma'am, why
Otherwise,
we
there
are
is no
adding
point.
these means both the solutions?
Yes,
Why we are adding them?
because they are linearly independent. Okay. For this one, we are getting two roots. Okay.
Ma'am, what is Wronskian?
Wronskian, I think I didn't put this linear algebra record. Okay. You should put it. You should have the linear algebra first. But it is there in the, I think, it's in the second semester. Okay. Wronskian, you see, it's a formula. Okay. You will find whether, you know, linearly independent. Do you know that?
No, ma'am, I don't know.
No, ma'am.
See, because linearly independent, so it's in the second semester. It's a long one. Okay, we'll be seeing that. The only thing you say from the name only you understand that. Okay, and how to know it is linearly dependent or independent, that you will be getting this one. See, what I'm saying. Suppose you have e power this m1x and this e power m1 m2, they are not equal. Okay, they are m1 and m2, they are not equal, and they are linearly independent. Okay, the like when you say y equals to fx, if they are not linearly independent, suppose this one e power m1x and e power m2x, they are not linearly independent, means you can express one in terms of other. Okay, you got it. This is the way. Now here this is one of the way to check whether it's linearly independent or not. Wronskian, and in this Wronskian, if you are using on two quantities, okay, this is always, it is like y1 y2 dashed, it is y1 y2, and here we have y1 dashed y2 dashed. Okay, this Wronskian is constant. Okay, it's a particular like we find it is this way. This is y1. Okay, or you can say dy1 by dx, this is dy2. So this is the formula for the Wronskian. If you have two functions, okay, you can check whether both the functions are linearly independent or not by finding its Wronskian. If it is 0, it is linearly dependent. If it is non-zero, it's linearly independent. Okay, so those two, so here we are checking this one. Okay, so you will get to know this one in linear algebra, which is in the second semester. It's in the second semester, I think. Yes, that's in the second semester. So if W equals to 0, linearly dependent. If W, the Wronskian not equals to 0, it is linearly independent. So, and this to find this, simply you understand that there can be more. Okay, here you have two solutions. There can be n number of solutions, and they can be linearly independent. Not now. Suppose you go for a cubic. Here we are quadratic equation. We are getting the second order. If you go for third order, the characteristic equation will be of what? It will be of cubic equation. Then you will have three solutions. Okay, if those three are linearly independent, then you will put it here, c3 e power m3x. Got it? So general solution, we are adding these two solutions, we are linearly independent. And if you have linearly dependent, like the next question, you have the real roots, and they are repeated. Okay, so there we can find this one of the solution. So this
How will we found the values of C1 and C2? They are unknown constants.
you will put it unknown constant. They're arbitrary constants, not unknown constants. Okay. If yx, and see, if I'm writing yx equals to c1 e power m1x, and for any value of c1 c2, they will be the solution. Okay, provided e power m1x and e power m2x are the linearly independent solutions. Then this, for any value of these two constants, you will that expression will give you the solution. The other way you can say, you can have infinite solutions. Okay, that way also, but only the constant. Okay, with respect to, it's kind of, if suppose you are saying x. Okay, we are saying e power x is the solution. If you are saying you have a second order equation, e power x is the solution, then what you are saying is 2 e power x will also be a solution, 3 e power x is also be a solution, kind of things. Okay, and suppose e power x, and here you are getting e power x 3x. So here you can also make it 4 e power 3x. So kind of this. Okay. So this expression, you change the for any value of these constants, you will be getting the solution yx. They will satisfy that differential equation.
I did not understand the constant part.
So it is like for any value of C1, C2, it's a general solution, okay, not a particular solution. We are finding the general solution. So any value of C1, C2, that they will be the solutions of that differential equation. See, because we are differentiating with the constant, okay, many times it will go to 0. So that's why the general solution was out of. Suppose we consider 2 e power m1x plus 3 e power m2x. So this will be a solution, and simply e power m1x plus 4 e power m3x 2x. So this will be also a solution. You got it?
Okay, ma'am, got it.
So general solution means for any value you put for this constant, they will be the solution of that differential equation. Got it? Differential equation. Okay, don't understand that it's a normal equation. Since we are going for the differential equation, we are integrating, so constant, there will be arbitrary constant. Since we are going for the differential equation, you put it in the equation, and you will see this will satisfy the equation. Okay, find out this y dash x, y double dash x, and put it in the equation. You will see it will satisfy the equation. Okay. And for this linearly dependent, this don't, it will be there in your second semester. We have the linear algebra portion. Okay. The only thing you say, linearly independent and dependent, it's like you see when we are talking about R, we have one dimension. You go for R2, we have two dimension. So there will be, you can express any quantity in R2. We need two things, right? So both X and Y, if you see, they are independent. Okay. So So if you want to express in R, you see, you need this only one x value. But in R2, you see, you need x and y, two values. So these two must be independent. Okay, order pairs maybe. So any point in but any two values, okay, this x and y are independent. Like any point if you want, okay, you need this x and y value. Got it? So here we have two independent values we need, and if you go to R3, then you will have in the space you need three values. Okay, so these are independent, linearly independent. This x is independent of y is independent of z. Got it? So these three are independent. Okay, you can say and here these two are independent. Here only one independent value. Now you additionally put here one more point. Okay, then it doesn't matter. You always get two. These two will be linearly independent. Got it? The minimum thing a minimum number of components you require to express that. Okay, got it? So in the dimensions are coming from this linearly independent thing. Okay, this keep this in mind. Okay, the properly and the proper definitions you will get to know in linear algebra. So we do one example or I write this. So here, if you go for the repeated roots, okay, we have the same equations here, and you can try in the same form. We will have here y, this one, okay, real and equal roots or repeated roots. Okay, suppose M1 is repeated, okay, here. Equal roots means we have b square minus 4ac equals to 0. For the equation am square bm plus c equals to 0. That's the equation 1. Okay, for this case, we have real and equal roots if this happens. Okay, so you can try here. You will be getting the solution e power. So we will directly consider m or m1. M1 be the solution, it's repeated. Okay, so m equals to m. These are the roots. So here the solution will be of this form. C1x plus C2 and e power m1x. So this is the solution here, the general solution. If you have the repeated roots. Okay. Because you see, if it is e power m1 x is the solution, or you can say e power m1 x will be the solution. One solution, since m1 is the root, e power m1 x is the solution. Okay, so you can put it in the our first order linear differential equation, and you can see. Let me write down. Okay, if you want this one, then I will do it next class. Okay, the second, third one. Okay, the second one we did real and equal roots. Then we have complex roots, and this happens if in the equation b square minus 4ac is less than 0. So here the solution will be of this form. Y of x equals to y. So here cos qx, let's say to sin qx. Or simply, if you want, you can also say Directly you can get A is a constant, B plus IQ, X plus B, where P plus IQ and P minus IQ are the roots of the auxiliary equation. Okay. So if you remember complex roots, if they occurs in conjugates, and X, if A is the root, then A bar has to be the root of the equation. Okay. So here this one and this solution here, P plus and minus IQ. So this is the solution. So this is the form, and if you use the Euler's form, that is form, then you will be getting this form. Okay. Okay, if you want, I will do the derivation next class. So you're coming at the 3 o'clock. Okay, so there 10, then we will do that time. I put the notice, I think. So today 3 o'clock. Okay, we will do this one that time. Okay, then it's time. So I'm doing so. These two one we will do it next class. 3 o'clock.
Excuse
And
me.
they are
Yeah.
also arbitrary constants.
C1, C2, yes. C1, C2 are constants. PQ.
And A and B are also arbitrary.
Huh,
Right?
AB are arbitrary constants. Okay, I'm ending the class. Okay, we'll meet 2 o'clock again.